We shall now begin the consideration of a special class of events known as independent events or events that are tied with the word and. And so we can also call them and events. In particular, an outcome is in event A and B if we find that that outcome is in both A and B. To illustrate in this example, let us say that we have the sample space given as the numbers from 0 to 9. And out of this sample space, we define an event A with the points 1, 2, 3, 4, 5, and another event B with the events 4, 5, 6, 7, 8. Our goal is to find the event A and B and subsequently determine the probability of A and B. Well, let us start with a visual. We have the sample space right here, and then we have the event A, and we have the event B. In the event that they have an overlap, where you have 4 and 5 both present in both events, then we have 1, 2, 3, 1, 2, 3, and then we also have 6, 7, 8 as pending points in the event B. So at this point, the event B will consist of only points that are in both A and B, which is the shaded point on your screen. So it has the events or the points 4 and 5. In other words, event A has the numbers 1, 2, 3, 4, 5. Event B has the points 4, 5, 6, 7, 8. So they have two numbers in common, which is 4 and 5. So it means that the event A and B has 2 points, 4 and 5, out of the entire sample space. So it follows then that the probability of A and B will be how many points do you have in both A and B out of how many points you have in the entire sample space. Well, in both A and B, we have the numbers 4 and 5. The count of that number, of those numbers, will be 2 out of how many points do we have in the sample space. In the entire sample space, we have 10. So the probability is 2 divided by 10, same as 0.2. You see, what we have just defined here extends to a rule in probability known as the multiplication rule for independent events. Whenever two events E and F are independent, then the probability, the joint probability of both E and F will be the probability of 1, probability of E, multiplied by the probability of F. To illustrate this idea, let's consider an example. In airline applications, failure of a component can result in catastrophe. As a result, many airline components utilize something called triple modular redundancy. This means that a critical component has two backup components that may be utilized should the initial component fail. Suppose a certain critical airline component has a probability of failure of 0.0064, and the system utilizes the component, and the system that utilizes the component is a part of a triple modular redundancy. Assuming each component's failure or success is independent of the others, what is the probability that all three components fail, resulting in disaster for the flight? To begin with, this assumption that this problem requires tells us that we're dealing with independent events. The assumption that all components' failure or success is independent of the others. So, if we're interested in the probability that all three components fail, we can see that as follows. we can write the probability that all three components fail will be the probability that the first component fails, and then the second component fails, and the third component fails. Notice the use of the word and here. This begins to take into consideration, or this is a reflection of the fact that each component and its failure or success is independent of the others. So, if the first component fails, I will need to look at what is the probability that the first fails multiplied by probability that the second fails multiplied by probability that the third component also fails. The big question is, why can I write probability of first fails times probability of second fails times probability of third fails? To emphasize, it is because the failure of the first, the second, and the third are assumed according to the question to be independent of each other. So I can apply the independence rule, which is probability of E and F is equal to probability of E multiplied by probability of F, provided that events E and F are independent events. So we continue here. So probability of the first fails was provided in the question. The probability of failure is 0.0064. So 0.0064, that'll be the first one, multiplied by 0.0064, multiplied by another 0.0064, same as 0.0064 to the power 3. And that will be equal to 2.62144 e raised to power -7. This is the same thing as write 7 zeros, 1, 2, 3, 4, 5, 6, 7. Put a decimal after the first and the second one, and then enter the numbers, the significant numbers, which is 2.62144. This is the full form of that number, if this is the initial standard form provided to you by your calculator. So with that, we make a formal introduction into independent events. Then we proceed to another type of event, namely complementary events. See, to illustrate, when we talk about the complement of an event, it is the set of all outcomes that are not in the original event of interest. So say, for example, if we're given the event A, its complement is written as A prime, or A with a superscript C. It is A with a C or A prime. Now, let's illustrate. In this example, we have the sample space are the points or the numbers on the face of a die. 1, 2, 3, 4, 5, 6. These are the possible outcomes. The only outcome that the event A takes in are 1, 4, 5, and 6. So we have the sample space, and we have event A, and in the event A, we have the points 1, 4, 5, and 6. So you have 2 and 3. These are the points left in the sample space. So as it stands, the event A is right here in the middle, and the complement will be all the other points that, if added to or if united with the events or the points in A, you will get the sample space. So the purple space is your A complement or A prime. So as it stands, the probability of A in this case will be, how many points do we have in A? That will be 4 out of, how many points do we have in the sample space? 6, same as 2/3. Whereas probability of A prime would be, since this is A, so let's map this out. A would be all of those points, so that would be 1, 4, 5, and 6. Then A complement would be in purple, which is 2 and 3. So as it stands, probability of A prime would be how many points are purple? That will be 2 out of 6, same as 1 over 3. Then, using the answer we got in part A, which is 2 over 3 for probability of A, and probability of A prime, or probability of the complement of A, is 1 over 3. It means that in part 3, we are required to find probability of A, which was 2 over 3, plus probability of A prime, which is 1 over 3. That will give 3 over 3, which is equal to 1. So as it stands, we realize that probability of an event A plus probability of the complement of event A will always give us 1. What does this mean? It means that it is certain. The probability of certainty is 1, remember? So it is certain that you either get the event or not that event. So what we would like to illustrate here, that picture is what we still have here. You can always replicate it here if you want. This picture right here can be replicated here if you want. So with that said, we move on to more interesting problems on probability. For the first example, we're told that a grocery bag can be classified as either plastic, paper, or plastic. Suppose that 80% of the grocery bags are classified as plastic. So, in this case, what this means is that probability of picking a plastic bag to begin with is 80% or 0.8, and that implies the probability of paper, since it's either paper or plastic, will be the remaining 20%, which is 0.2. Now for question A, 2 grocery bags are chosen at random. What is the probability that both grocery bags are plastic? So, as it stands in this case, if I pick the first, based on the description of the problem, we're told that 2 grocery bags are chosen at random. If truly this is a random pick, then the bag you select on the first pick is independent of the bag you select on the second pick. So what that stands to mean is this, that we're dealing with a case of independent events. So probability that 2 grocery bags, in this case, are plastic, this will be equal to probability that first bag is plastic and the second bag is also plastic. Since they are independent events, based on what we learned about independent events earlier, I can split the probabilities into individual probabilities, and then multiply them together. So let's apply that here. So I can split this into probability of first bag is plastic, multiplied by probability that the second bag is plastic. And we have been provided with the individual probabilities here. It is 0.8 multiplied by another 0.8, and that will be equal to 0.64. Then next, we're told that 9 grocery bags are chosen at random. What is the probability that all 9 grocery bags are plastic? This is very similar to what we just done. Probability that 9 grocery bags are plastic will be equal to probability that first is plastic multiplied by probability that second is plastic, up until the last one, which is probability that the ninth bag is also plastic. So this will be equal to 0.8 multiplied by 0.8. Let me raise this up. So we'll have a case of 0.8 multiplied by itself 9 times, which is same as 0.8 raised to power 9. And that is equal to 0.134217728. Then we proceed to question C. What is the probability that at least one of the 9 randomly selected grocery bags is paper? Okay, let's stop reading at that point and let's answer that question. Then we'll be back to the second part of the question. First of all, you should note that the probability that none plus probability that at least one is paper is always equal to 1. This is always true. This is a key point to note because these are complementary events. You either get none of something or you get at least one of that thing, of that group or set of things. It is either you pass on none of your traits. It's either you pass on none of your items to someone else or you pass on at least one to that person. This is a certainty. So with that said, please note this formula is extremely useful whenever you're dealing with problems that deal with at least one. Now, it's either we have none, probability that none is paper is the same thing as probability that all 9 are plastic. So we have the answer for that, which is 0.13421. I'll just take it to 5 decimal places. So we had that answer given earlier. Probability that none is paper is the same thing as probability that all 9 are plastic, just to emphasize, plus the unknown. I'm going to call it X. Remember, probability that at least one of the 9 is paper. That is equal to 1. So I can subtract 0.13422 from both sides. And so my X is equal to 1 minus 0.13422. And that will be equal to 0.86578. This is the probability there. Now the question, the latter part of the question is asking, would it be unusual that at least one of 9 randomly selected grocery bags is paper? That means we need to check if this answer in this context is less than 0.05. That is the question. As it stands, it is not less than. So since it is not less than 0.05, it is not unusual. Since the value of the probability that we just got is not less than 0.05 for the context of this problem. So with that said, we proceed to another example. Students who live on campus and purchase a meal plan are randomly assigned to one of 6 dining halls: the Commons, Northeast, Fraser, Tilton, Bush, and Carmichael. What is the probability that the next person or the next student to purchase a meal plan will be assigned to Northeast? What method of computing probabilities did you use? In computing this probability, what I would note is that this is almost similar to having an orange split into 6 equally sized pieces, and I have all possibilities. You have the Commons, you have Northwest, you have Fraser, you have Tilton, you have Bush, and we have Carmichael. And so the probability that the next student will be assigned to Northeast is taking one chunk or one slice out of 6. So the required probability here would be 1 out of 6. Notice that in computing this probability, What I did was to consider the possibilities. I did not actually assign a student to Northeast. These aligns with what method of computing probabilities? Do you recall? That would be the classical approach, in which case you used to consider all the possibilities without actually carrying out the experiment. You look at number of ways the event can occur, and you also consider the fact that all the events are equal, or all the outcomes are equally likely. So in this case, we'll be using the classical approach.